instead of
I know a lot of you have more questions about the related rate stuff, especially number 18. I've heard your questions. The whole solutions will be hopefully up tonight or sometime shortly soon. And we can certainly engage in more questions on those if we have time today or another time soon here, hopefully. All right, we're going to talk about something called Newton's method. Again, I think that even though that you might get caught up a little bit in some of the notation, it sometimes looks a little confusing on the onset. I want to make sure you understand that the idea behind this is quite simple and easy and intuitive. And it will be a nice respite from optimization or related rates. Right? So we've done the two intense parts of this unit here. Optimization and related rates. The thing that kind of makes this unit notoriously thorny. This is not too bad, I promise. We're going to come down from our hill here. So it's fair game on any AP problems from now on for the rest of the year. All right, or related rates. Okay. All right, so this is, of course, everything has Newton's name on it in life, as you know. So this is one more thing that Newton gets credit for, even though I'm sure he's not the only person who thought of it. So this is, in fact, what we're gonna actually use a root finding method here today. It's a root finding method algorithm, and it's the one that your calculator uses or something like it. And so we're gonna illustrate with a function, just so we can see how this works. With a function first that you already know the zero of. Like you don't need this method for this particular problem, right? You could find where f of x equals 0, or rather the two places that f of x equals 0 on your own. But we'll compare. Imagine I give you this function. You have no way of finding the solutions to this equation, do you? Without the use of root calculator. So we want to start with an example that we can do both ways. So we're going to start by looking at the graph. We're going to be looking for this root over here. And this starts just like your calculator does. You may have wondered in your life, why does my calculator always make me start with a guess? Doesn't it always make you guess first? Okay, so this algorithm starts with a seed of some kind to seed the process. Okay, so we're going to start with a guess. I'm going to zoom in just around the area of interest here, or the right root. By the way, f prime of x is x, in case you wanted to know that. Because you know that. There you go. You're welcome. We're going to start with a guess, and I'm going to guess that the root is 3, say. Say that's the starting guess that I made. This process we're about to engage in relies on something very simple, and that's the linearization. So what I'm going to do is I'm going to construct the linearization at x equals 1.5, at x equals 3. So there it is in red. And notice that my guess right now can be quantified in terms of how good or bad it is by seeing when you plug it in whether you get something that's close to 0 or not, right? And right now, like if I made the perfect guess, if I plugged it in, I would get 0. But I don't. When I plug 3 into this function, I actually get 1.5. So we're definitely not there yet. We've not arrived. But we can build a linearization from that point. The tangent line has a slope of 3 because we're at x equals 3, and the derivative happens to be x. So the slope of that line is 3. So I don't know, how off are we here? We don't have to build the whole linearization necessarily, but let's think about the amount that we're off by. What would we have to kind of subtract off here? Let's call that amount right there that we're off by an amount called z. Well, that's 1.5. And if the slope is 3, can we figure out what z is? Sure we could. The slope is 1.5 divided by z, which is 3 apparently. So z is 1.5 over 3. So notice what we've done here is we've said, okay, well, this linearization hits the line here. If we pretend this is a line, we don't have to find the 0 of that. Our new guess is 2.5. It's better. Guess what we're going to do again? We're going to do this a second time in a minute. Okay, so just want to make sure you're highlighting what we just did down here. This is the calculation we made. We took our guess, and we did our guess minus, what was 1.5? Take your guess, minus f of your guess, divided by f prime of your guess, and that generates your new guess. Have you seen this before? That's the warm-up, right? That's you finding the zero of your linearization, right? It's just, so you can also just memorize guess minus f of guess over f prime of guess. But know that all that is just the linearization, you finding the zero of your linearization. And the answer is, it always comes out to be your guess, your old guess, minus f of your guess over f prime of your guess. Every time. All right, so what do you think we're going to do next? We're going to do the whole thing again with a new, better guess. We're going to start with 2.5. We're going to find f of 2.5 and f prime of 2.5 and do this again. So here we go. Now we're at 2.5. This is our new, better guess. Now we're here. Now we're at this point right here. 2.5 comma, apparently, 0.125. That's our new spot on the function. And we build, notice this little tiny linearization in here. We build another linearization and say, hey, the function basically acts like a line. This is like our one move in calculus, right? We only have one, there's only one game in town. Let's pretend it's a line. Because we know how to find the zero of that. We're really good at finding zeros of lines. We like that. We have no idea how to find the zero of some crazy function, though. So let's just keep pretending it's a line and generate for ourselves better and better guesses. All right, so let's go through the process here. We need, what do we need? We need the guess. We need f of the guess. We've got it. And we also need f prime of the guess, which in this case has been nicely set up for us, so that's a nice thing. That's, of course, just 2.5 again. And of course, this, maybe in some ways you might be thinking that's an unfortunate way to start out here, because you might always think that this is like the same as the guess. But of course, that just happens to be true for this problem. But in general, it would be whatever f prime of your guess is. Well, we just copied and pasted this slide from the last one. This comes again from the warm-up, right? How do we find the zero of this linearization? It's your guess minus f of your guess over f prime of your guess. You see, feeling this? Guess what we'll do with that?
Do it again.
Do it again. Notice how good we're getting. Is 2.45 the root? No. But if you plug it in, you get something that's awfully close to zero, right? And this, we can make this arbitrarily good. So I don't have anything to add. We're just doing this again. Here's our new guess. Ben?
I give up.
Not close enough.
Isn't that close enough? That's a good question. By the way, let's just keep track. How many guesses do we make? Let's call the first guess before we did any work x0. Would that be a good name for it?
Yeah. Well, no.
No, I don't think so.
All right. Then after doing our process once, we might call that new guess, which was the first x0 was 3. Was our first guess. X1 we might call our second generated guess. It's not really a guess anymore, but it was generated from our original guess. After one iteration of this process, we got x1. Was 2.5, if you remember. And then we did it again, and we generated x2, which was 2.45. And then x3 is what we'll call this terrible number down here. 2.449, etc. And it is pretty good. It is a pretty good guess. In fact, let's just stop there and see that if you plug in this answer, you get something that's basically the zero of this function, right? And if you want it to be better, feel free to keep going, right? Do another iteration. But this, only after 3 times doing this process, you should be impressed that we did x0, and we did one process once, x1. It's a very cute little tiny process involving only subtraction and division. It's not like a huge taxing thing for you or a computer to think about or do. Or Newton, back before computers. He could do this. Only after 3 iterations we get a zero that's like wicked good. Yeah. How many should we do? Where should we start? These are all good questions. Yes? Yeah.
Why does your calculator make you go through a bunch of
It doesn't. Not for zero finding. Yeah. All right, so Newton's method, if you haven't already seen, is an algorithm, and it's a special kind of algorithm that uses the input from the last step and the output from the previous step. So any mathematician who studies recursion or any computer scientist who likes to write programs that are iterative like this would tell you that this is called a recursive algorithm. It uses the output from the previous step in the calculation for the next step. And each run of the algorithm is called an iteration. So I think the way we've subscripted these is really helpful, right? X0 is our initial guess before we've actually done an iteration. X1 is the result of having done one iteration. X2 is the result of having done two iterations. But notice there are really three guesses. So your first step is to come up with a guess, or sometimes we'll tell you what the guess will be. Something just so we all have the same process. A graph may help. And then this is what we've been doing, right? Our next guess, that is x sub n plus 1, is equal to x sub n minus f of x sub n over f prime of x sub n. That's just the thing we've been doing. And that's the thing that Ashley put up on the war on today, isn't it?
Oh wait, was that me?
Yeah, that's just the warm-up. And you thought that it was useful. All things with purpose.
Oh wow, don't have application.
Okay. What? What happens when what? Oh, what happens when you start from 1,000? Yeah, you should try it. I think you'd be surprised. I bet it won't take more than, 10 iterations to get through it. Close. It is a similar process. It uses something called a little bit called gradient descent. They use this very similar algorithm. It's a recursive process that makes guesses. All right. Are there any procedural or conceptual questions so far? I'm gonna make this slide go away in a second, but the big idea is this box right here. Start with x0 and then apply this little algorithm over and over again as many times as we tell you, or as many times as we need. Sometimes we'll tell you run it for a couple iterations. We'll say run it for 3 iterations. But a lot of times what we'll tell you is run it until it stabilizes to 3 decimal places. Approximate the root to 3 decimal places or something, right? And what that means is do as many iterations as you need to have the root in your possession, right? To write to 3 or 4 decimal places or something. So, and then you just go until it doesn't change, and then you say, okay, well the previous step was how many iterations it took. We can be done now. Here's a nice animation that shows what we've been doing. So we're trying to approximate that root. New guess, linearization. Uh-oh, now we're over there. Is this gonna work? New guess. Let's watch it one more time too. Pretty good after 4 iterations. Let's watch it again. So I just want to make sure you're clear. This is all that we're doing is using linearizations to continually get better and better. Yeah, did you notice what happened there? It was a little less tidy than the one we did. It jumped across for a second. That's okay. In fact, you might have questions about whether this will always work and whether it will always converge to something. I'd like you to start thinking about where this could maybe go wrong. Yes. Yeah, we'll be very specific.
The maximum amount of guesses that we should use.
Yeah, you'll see in the homework even tonight. Yeah.
So, like a recommended,
I don't know. Maybe
Recommended deviation from the guess? I mean, as soon as you get a new guess, the amount you're going to change your new guess by is determined by this linearization. There's your new guess.
Oh, yeah.
There's your new guess, right? So you don't have any more
Whatever
choices.
you get, that's what you use for your
Yeah, exactly. So once you make your first guess, your choices in the process are done. All right, let's do another one. Notice that this is an example now. Finally, on the last one we didn't even bother to check really what we didn't use algebra. But on the last one we could have used algebra to actually figure out what the actual root was. Here, notice that x cubed minus x equals 1 is not an equation you know how to solve symbolically. As simple as it might sound, x cubed minus x equals 1 is in fact one of these equations. So I'm gonna show you too here a way to kind of help set up your work. First of all, hopefully it goes without saying that the equation we really desire the zero of is this equation. So notice, if it's not obvious already, that this is not just a zero finding method. This is an any equation solving method, right? Because all you have to do to solve any equation is just find the zero of a particular function, right? So finding zeros is not just like a little thing, it's everything, okay? So let's find the zeros of this function. And when we do, we'll have the solution to this equation, okay? So this is the function of interest, and we're looking for the zero of that. We'll need the derivative. Are you okay with all the things I've written up there?
Yes.
All right, now we're going to set up a little chart to organize our work and our guesses. I'm going to tell you to start with 0. With 1. Did I tell you 1? Did I'm telling you 1. I'm giving you the first guess.
First guess, okay.
So that's x0, right? We have not done any work yet. I'm giving you that. Now you can see that we have lined up here the things we need. We need f of 1, which is negative 1. 1 cubed minus 1 minus 1. We also need f prime of 1. What's that going to be? 2. And then we also need our next guess. And that's, what is that? That's this. That's our original guess. 1 minus 1.5. So that goes down here for our second iteration. Here we go. Now we're ready to go into our second iteration. This is x1, 1.5. Do it again. There will soon be a need for the calculator.
No, I use them really.
Get 0.875. And from the derivative, 5.75. We'll do. So we've done 2 iterations now.
That's what I got. Yeah.
X2 is x2 after having done 2 iterations is this 1.348.
That's what I got.
Yeah. It's actually super important that you use a calculator. One of the things that we're gonna turn to in a minute here is how to really well use your calculator. How to really efficiently. Sorry. How to use your calculator really well. I think the subject, the object, the predicate, all of it were there, just not quite in the right In many languages, it doesn't matter what order you say.
Well, like Shakespeare. What languages is that?
Like Japanese, you say the subject, then the object, then the verb.
Maybe that matters. You can't say the verb or the
You
object.
can actually say it any order you like. You can say the object, and then the subject, and then the verb.
But then it changes.
You actually use a marker. Why? There's a word that marks the subject. All right, so I'm going all the way here. Notice that our final number here is, again, if you plug it into x cubed minus x, gets you a value that's pretty close to 1, right? Which is the thing we originally asked about. So this, I think, is not a bad approximation for our solution to this equation. And how many iterations did we do here? Yeah, let's make sure you understand, even though this looks like maybe 2 or something. This is 3 iterations, and even though we don't have another row in the table for it, this is x3, right? Everyone clear on that? So this is x0, which I gave you at the beginning. This is x1, which we generated from this algorithm. This is x2, and this is x3. Yeah.
How do you know when to stop?
Again, I haven't covered that in particular, right? So the instruction will either, usually, one could, I guess, just say do 3 iterations or something.
No, you know when to stop.
But we'll say, often we'll say, estimate the 0 to 3 decimal places or something like that.
We need to go another time for this.
We would have to go one more time if it was said 3 decimal places.
So you have to have the same 3 decimal places.
Yeah, once it stabilizes, yeah. But I think you're going to see on the calculator here that there's a really nice way to make this happen really quickly and do as many iterations as you like. I'll show you. All right, couldn't I just use the calculator? I guess by the calculator, I mean, couldn't you just use the zero finding method of your calculator? What's so wrong with that? Because obviously you can't do this without a calculator in your hand anyway. So couldn't you like cheat and just like find the 0 using the already built-in algorithm on this? And the answer is like kind of yeah, but here's my explanation. Sometimes this actually comes up on a non-calculator portion. It's just we can't ask you very many iterations, right? So we'll even have you do that too in this course as well. We just have to only do like 2 iterations or make it set up so that it comes out really nicely or something. On a calculator question, we might be asking you to do this too, and you would just need to show your work that you're using the formula. So let me show you what I would actually do on the calculator, okay? And I'll pull up my calculator and do it in a minute. But do this with me, will you? In your calculator, this is the one we just did. I just want to show you a nice, efficient way to do this. Put this in y1, x cubed minus x minus 1. Go ahead, I'll give you a second. We'll use 1 as our guess. Once it's in y1, go back to your home screen and type in the following on your home screen. 1 store x. And I want you to use the letter x on your calculator. 1 store x. So go back to your home, once it's in y1, go back to your home screen and type in 1 store x. Store is above your on key.
Like this x or the letter x? Like
They're the same.
They're the same?
And press enter. Okay? Then then put the derivative in y2, go back to y equals, your y equals, and put the derivative in y2, which is 3x squared minus 1. I really want you to practice this, because this is not just a demonstration. This is going to be critical for you. I only have 2, but I can give them to those who need them. Alright, so does everyone have in y1 the original equation, in y2 the derivative, and on the home screen you've typed in 1 store x, press enter, okay?
Wait, where's store again?
Store is above the on key. Alright, now on your home screen, guys, type in x minus y1 divided by y2. Store in x, all in one line. Do you know how to get y1 and y2? Go to second vars. Oh, sorry, vars. Y1 function y1. Y vars function y1.
Okay.
Yeah. So what does this do? Can anyone? Where are my computer science people? What is this gonna do? Go for it. What does it do? What is this here? Look at the right. Look at the left side first.
You just spam enter. You just spam enter.
This is Newton's method on the left, right? And then, so I know this seems weird, but it says, it's like saying, take this value and store it in x. Yeah, this is not an equal. This is not an equal sign. It's not like saying this is equal to this. It's saying.
Jasper, come on,
All right, all right, listen here. So, yeah, this is doing the Newton's method algorithm we talked about earlier. When you're done and it generates a guess, it's going to store it in x, and the new value of x will be the new guess, right? So this is not an equal sign. It's not saying this is equal to this. It's saying this will be the new x. It's assigning it now to the value of x. And now x will not be what it used to be.
I didn't know if you calculated initialize a variable.
Yeah, I mean, the reason I say that this is, so, you know that, like, this is like an anathema in anywhere else. But like when you're doing computer programming, the store goes this way, actually, right? This would be, if you want to advance a variable, you'd be like, let t be what t was plus 1 or something like that, right? And that's a very different understanding of the use of the word equals than we use in mathematics, right? Like that's like, take this and store it in that. This t and this t are not the same t. Yeah.
I did not get that.
All right, but notice you can just keep pressing enter and get as many iterations of this as you want. Once it'll start stabilizing right away, right? I mean, after like 3 or 4 iterations, yeah, you've done like a million iterations, right? What is it? Minus x plus minus 1?
Minus x minus 1.
All right, here we go. So we're doing 1 store in x, and now here we go. X minus y1 divided by y2 store in x. All right, so let's just make sure we're keeping track, guys. So thanks for listening. Well, x0 is this. x1 is 1.5, x2, x3, x4, x5. You can see how efficient this is. And notice already when we're at, is this x6 now? That we're already to 9 decimal places, we have the 0, right? All right, let me give you the handout. How's it going, Natalie? How's the calculus? Wait, what?
Think of the kids.
Who are you here for? This guy? Sorry, did I sit at your table? Sorry. Hope you don't take it personally. Did you guys, Derek, did you get one?
Neither am I.
Did you get a worksheet?
I gave you one.
I would have tweaked the vocabulary.
Yeah.
It was it's like, I was interested in math. I was still like,
Yeah. Well, you're taking it.
I think
Next year? Oh. Right. And then next year, you're going to take what?
I was going to take stat.
Oh, you haven't taken any stat yet?
No, I didn't have
That is good, but you can do both, you know.
So like I want to be multivariable.
Roll out.
Bye, guys. Have a good weekend.
Thank you, you too.
Right. Yeah, well, that's true. I don't know that.